So whereas the first part was the indefinite integral, the second part that we're going to look at is something called the definite integral. And the idea of the definite integral, and my little squares here, well, Word went a little crazy and they're not matched up. But I think on yours they're pretty nice, that your little rectangles are nicely inside. So the idea with the definite integral is integration can provide us with a way of finding an area under a curve. Now, if I wanted to find the area under, this looks like some sort of sine or cosine graph, you'd be like, I don't know how to do that because that's so curvy, and I know how to find areas of rectangles, I know how to find areas of circles, I've got formulas for the area of a triangle, but I don't have formulas for areas of some sort of thing under some sort of crazy curve. The definite integral provides us with that, because what it does is it says, instead of finding that whole area, what if we broke this up into rectangles? And you can probably see it on your paper better than this one, but those rectangles are pretty close to the actual area. I think each of the rectangles is a little bit below, so you'd say your area is not quite there. It's just a little bit less. But if I made my rectangles smaller, wow, there's one, keep switching colors here. There's a second rectangle, and then I do a third one. Can you see that that would be more accurate? And if I kept going smaller and smaller and smaller, eventually that area would be perfect. And so that's the idea of the definite integral. What the definite integral does is it creates those smaller and smaller and smaller rectangles so that when you evaluate it, you actually get the perfect area underneath that curve. Now, we don't go deep into the theory. If you want to read up more of the proof and stuff like that, or if you want to take the advanced math and calculus, we look at that a little bit more in depth. But for right now, what we're going to take from that is just the general idea that what that does is it makes those rectangles smaller and smaller. And if you add up all those small little areas, you will get the area of the whole thing. And the way that it works is we add some values to our integral. What those values are is a lower bound and an upper bound. Where do you want to find the area from? So from here, if you wanted to find the area from A to B, the A would be on the bottom of your integral and the B would be on the top. So, how does this work? So the dx, that's the limits of A and B. A is our lower limit, B is our upper limit. To find out this definite integral, we start by finding the indefinite integral. So we integrate like we've been doing so far. We don't even worry about the plus c. We just do the value without the plus c. Notation-wise, we're going to write whatever our integral is in square brackets and put our a and b on the outside of those square brackets. So that's just notation. Then to find the actual area, all we do is subtract f of b minus f of a. So I'm going to take a really simple example. You don't have to write this down, but show you something that you would know how to calculate and how it works. Okay? So don't write this down, but we're going to take there's y equals x plus 2. It's a straight line. And if I wanted you to find the area between 1 and 3, you could do this without integration, without calculus. Because of the shape, can you see that it would make a rectangle and a triangle? And what do we know about our rectangle? Well, this point here is 1, 3. This point here is 3, 5. So what do we know about our rectangle? It has a length of 2 and a height of 3. Would you agree that that area is 6? And what do we know about this triangle? It also has a length of 2 and a height of 2. Base times height divided by 2. Would you agree that that area is 2? And so the whole area from 1 to 3 of this shape is 8. So how does this work with the definite integral? Well, the definite integral says we can integrate our function x plus 2 dx from 1 to 3. This is an easy integral to do. How do we do that? Well, add 1 to the exponent, divide by 2, plus 2x. We don't worry about the c. We put it in square brackets, and we say we're going from 3 to 1. The next thing you do is you plug in 3. So if I plug in 3, I'm going to get 9 over 2 plus 6, right? And then if I plug in 1, I'm going to get 1 over 2 plus 2. And if I subtract those two, well, 9 over 2 minus 1 over 2 is going to be 8 over 2. 6 minus 2 is going to be plus 4. 8 over 2 is 4 plus 4 is 8. The same area that we had from before. Now, this one is not bad because we could have done old strategies from before to figure that out. But now if you put a parabola there, you can do the same thing and find the area under the parabola. And if you put a sine curve or anything that you want, we can now figure out that area. Because what the equation says is you start with this. You find your integral, and then you just plug in b, subtract, plug in an a, and get your answer. Now, normally when we're doing this, we do have a as our smaller value and b as our bigger value, but you can do it backwards and get negative areas, and it still works theoretically, although it doesn't work as well if you're thinking about what it actually means. You can do this as well on your graphing calculator. So you can graph your function. So let's take out our calculator and just graph the one that we did, x plus 2. So there's x plus 2. Second, calculate number 7. It says, what's your lower limit? We want to go from 1. What's our upper limit? We want to go to 3. And it even shades it in there nicely for you and shows you that area, that the area is equal to 8. So if you're asked for a definite integral on your exam and you got your calculator, boom, this is a lot faster than actually calculating it all out. So depending on the situation on the exam, it could be really useful. There's some other things that you can do in your calculator. So if you go and hit your math button and go to number 9, to F integer, it actually comes up like this. So we can say, what is the integral from 1 to 3 of x plus 2? You do need to tell it that what you're integrating with respect to, and it gives you the answer that way as well. I like the graph because it shades it in and it's kind of fun. But
how do you put that on older?
so if you have the older calculator, I think I have it in the notes here. You put your function, comma, you have to put x, put your lower bound, and then your upper bound. Now, for your exam, you don't use your own calculators, you use the school set of calculators. And right before our exam, we're going to do a quick check to make sure that they're all upgraded to the newest operating system, because it is a lot nicer if it appears like that than if it appears as some mysterious string of things you have to put in.
Are they all like are they any of those older ones, or are they all like?
They look like this. So, I don't know where the little X went. If that's missing in your notes, you can add that X in there. No, it's not. For some reason, it's just missing in mine. Evaluate the following integrals. So, this is going to be equal to, well, we integrate the 3 over x like normal. 3 over x, the integral is 3 natural log of x. Notation-wise, we put our upper and lower there from 5 to 2. And then to evaluate it, we plug in 5, then subtract, plugging in 2. And if there was no calculator, you would leave your answer like this. If it was calculator, you could plug that into your calculator and find out what that actual value is. What have we done? What does 3 over x look like? It's your 1 over x graph stretched by 3. What are we doing? We're plugging in from 2 to 5. We just figured out what that area was really quickly, which is kind of cool considering how that thing curves and how easy that was to do. I don't know why all these X's disappeared on my notes. Do you see that you have an inside function? That x squared plus 1 over x is inside the squared. But if you did the derivative of that, does that appear in this at all? The derivative of x squared plus 1 over x is 2x minus x to the negative 2. I don't see that anywhere in my function. So substitution, even though I have a function inside of another function, is not going to work. Any other ideas? Thanks, Mr. JR, for providing an idea that doesn't work. Okay. Good, good. We would have to multiply this out. So I'll keep the notation here. When I multiply this out, I'm going to get x squared plus 2 plus 1 over x squared dx. And now each of those are easy to integrate. We're going to get x cubed over 3 plus 2x add 1 to the exponent and divide. Now if I plug in 4, I'm going to get 64 over 3 plus 8 minus, and that would be 1 over 4. Subtract. Plugging in 2 will be 8 over 3 plus 4 minus 1 over 2. Sometimes what I do in these questions, instead of getting a common denominator from everything, I just put some of the things that are close together. Like 64 over 3 minus 8 over 3. Can you see that that's going to be 56 over 3? And 8 minus 4 is going to be plus 4. And negative a quarter plus a half will be plus a quarter. So I do that because sometimes the things simplify out nicely that you can figure everything out. In this case, at this time, if I want to add this all up, I will need a common denominator of 12. So if I multiply this by 4, I'm going to get 224 over 12 plus 48 over 12 plus 3 over 12, 275 over 12. Did someone do it on their calculator to check what the answer would be? So I can go back to this now, and I can go to my graphing calculator. I can go Math 9 and type in my original equation like I have. We were figuring it out from 2 to 4 of x squared, x plus 1 over x, was it? X plus 1 divided by x to the power 2 dx. So we can write in our original function just as it showed up. We can push enter. It's going to give us an answer. If you go math, fraction, we'll find out if we made a mental math error along the way. Fortunate for me, we didn't. And so the answer is 275 over 12, which is 22.9. And again, if you graph this x squared plus 2 plus 1 over x squared, you just found the area underneath that curve to the x-axis from 2 to 4, which is kind of crazy. Okay, here's one for you to try. All right. How did you do? You get your integral right. Then you plug in 1 and subtract. And now when we have more than one thing, like in our integration has 2 terms. So notice I put one big set of brackets when I plug in the 1, put a subtraction sign in between, and then one big set of brackets when I plug in the 0. Simplifying this. And here's a picture. Well, keep it like that. There's a picture of the area that you just found on that interesting looking graph. So as far as integrating goes, going from pi over 6 to pi over 2, as far as integrating goes, what gives us cos? I mean, what gives us sine? What derivative gives us sine? Because I find that with sine and cos, this is where you're going to get things mixed up. Because there's a negative with, right? The derivative of cos is negative sine. The derivative of sine is positive cos. So now working backwards, those negatives get all mixed up again. So what I find for me helpful is I only remember one thing one way. So I remember that if I have sine, my tangents start out positive, so the derivative of sine is positive cos. And if I have cos, my tangent starts at 0, but then will go into the negative, so the derivative of cos is negative sine. And then when I'm working backwards, I say, okay, well, sine is going to have to go to cos, but cos to sine is where the negative happens. So in this case, I'm going to get negative cos 3x, and I have to divide by 3 because I have that constant inside of my function. You could use substitution for this one.